Hello everybody. In our series of lectures on basic electronics learning by doing, let us move on to the next. Before we do, as usual, it will be nice to recapitulate what we discussed in the previous lecture. You might recall that we discussed about the inverter, non-inverter circuits, the switchable inverter circuit, the non-inverter circuit, and then JFET, the junction field effect transistor controlled switchable inverting circuit amplifier, and then inverting amplifier with adjustable gain. And we also saw the sign changer, how you can either make it plus or minus, that is 180 degrees out of phase or the other way. And then we also looked at adjustable and reversible gain. We can go from, for example, a gain which is minus 100 up to plus 100 by moving a potentiometer. We also saw at the end how a phase shifter can be built using operational amplifier. All these circuits we saw under what I would call as application circuits of operational amplifiers. Now, let us move on to further application circuits of operational amplifier, and one which perhaps we would be discussing today is what is called instrumentation amplifier. In many instrumentation applications, you would find you will have very low signals from maybe some sensors or transducers, and you would like to amplify them and then read them for either control or measurement. So, in such situations operational amplifiers are very useful. There are some specific configurations which are called instrumentation amplifier configurations, which we would discuss, and they have certain specific advantages over the normal operational amplifier that we make use of. There are instrumentation amplifiers that you can also commercially buy from the market, and some of them are very good, but they are also very expensive. So, what I am going to do today is just to explain to you how a simple instrumentation amplifier configuration can be built by using standard operational amplifier. The one we normally discuss is the 741 operational amplifier, which is very popular. Right, instrumentation or amplifiers are used in several applications, from simple motor control to data acquisition to automotive circuits and things like that, and we will study only the fundamentals, basic functional configurations of instrumentation amplifier. We also see 2-3 configurations, how each one is an improvement over the previous one. Of course, it is to be mentioned that not all amplifiers used in instrumentation applications are instrumentation amplifier. There could be other types also, and in the same vein, all instrumentation amplifiers are not all the time used only in instrumentation amplification applications. You can think of other applications for instrumentation amplifiers. The basic idea behind the instrumentation amplifier is that it should have very high gain and it should have very good CMRR. You are already familiar, I explained to you what CMRR is. CMRR is common mode rejection ratio, which we know is the figure of merit to tell us about how good is the amplifier in rejecting signals which are common to the two inputs and preferentially amplifying only the different signals. So, this is a very important characteristics of every differential amplifier, and operational amplifiers being a differential amplifier, they have to have good CMRR. If you have a very high CMRR, then that is one of the criterion for a good instrumentation amplifier. The normal typical value of the CMRR for 741 you all might know is from 70 to about 90 dB in decibel units. You all know what the decibel unit is, we have already explained, and therefore, if you look for very specific instrumentation amplifiers, they will have very high CMRR. For example, 110, 120 is very common in instrumentation amplifier. 725 is one good instrumentation amplifier which has got CMRR around 120 dB, which is in if you calculate in terms of 20 dB per decade, it will be 10 power 6. That means it will amplify differential signals 10 power 6 times compared to the common mode signals, because you know the CMRR actually gives you the ratio of the differential gain to the common mode gain. So, it will preferentially amplify different signals by nearly 1,000,000 times. So, that is a very wonderful number, and therefore, they are very useful in several low signals and very on a noisy environment, because you know noise signals will be common to both the inputs, and that way the noise signals become the common mode signal, and this CMRR tells you how good is the amplifier in rejecting all those which are common, and in that sense the noise performance of the amplifier will be excellent when you have very high CMRR. But CMRR also will depend on the frequency and several other parameters, and so one has to be you should take note of this point, that the CMRR that we normally talk about are for low frequency applications. Right, now you can see on the screen the one of the simplest configuration of an instrumentation amplifier, and that, as I already mentioned to you, is a very simple differential amplifier which we have already discussed and seen. So, this amplifier, you have V in and V in 1 and V in 2, they are actually the common mode signals which are applied, and if it has got a good CMRR, you know these are all going to be rejected, and what is going to be amplified is only the difference in the signal between these 2 points, and that will be amplified by the differential amplifier. And you might recall we have also derived the expression in an earlier lecture. The gain of the amplifier is minus R2 by R1. I have deliberately, if I keep all these R2 prime and R2 equal, R1 and R1 prime equal, then you can have, for example, the ratio R2 by R1 about 100. This can be 100k, this could be 1k, R1 can be 1k, R2 can be 100k, then minus R2 by R2 by R1 will be 100k by 1k, which is about 100 times, and therefore it will, the gain will be 100 multiplied by the difference in voltage between the 2 inputs. So, this is a very simple configuration of an instrumentation amplifier. Okay, so that is precisely what I am saying here, but what I have considered here is if R1 is equal to R1 prime is equal to R2 prime and R2, and all of them, if I make them 100k for example in a typical situation, then the differential gain is only 1, because minus R2 by R1 in this case, because all the resistors are 100k, it will be minus 1. Hence, the input impedance of the V in input will be 100k, while that of the second one will be 200k, twice 200k, and therefore, you find the 2 impedances are not equal. This is one of the very important considerations in the instrumentation amplifier. So, you find when a simple differential amplifier is considered, the impedances at the 2 inputs are not equal. Because of that, you would find even the differential amplifiers will and the common mode signals, they will generate different currents through the input impedances, and therefore, because of the differences in the impedances, even the common mode signal will introduce a differential voltage, and that also get amplified along with the other differential signals, and therefore, you would get the CMRR will be brought down because of this. So, one should take note of it, that the 2 inputs, because they do not have same impedance, there will be a degradation in the performance of the amplifier. It will bring down the CMRR. Apart from that, there is another source for bringing down the CMRR in a simple differential amplifier that we are discussing, and that is basically to do with the tolerances of the resistors that we use in the circuit. See, we all know all resistors that we make use of in the lab, they have a specific tolerance. What I mean by the tolerance, you know, there will be a silver line or a gold line at the end. You have in the color code, you would have studied that you have first three color codes are corresponding to the numbers and the exponents, and the last one, the fourth one, normally is meant to indicate what is the tolerance of the resistor. That means, for example, if it is silver, it is 10%. That means what? If I take 100k the value of that resistor can be 10% plus or minus with reference to 100 k. So, if the tolerance is going to be different, what you say as 100 k in that case in the circuit may not be 100 k, it can be 90 k or it can be 110 k or it can be any value in between, and therefore, these differences in the resistances due to the tolerance can also lead to slight differences in voltages at the input and the output, and therefore, that will also bring down the CMRR, because these differences will start giving a differential signal for the common mode signals applied to the two inputs, and that will lead to an additional differential signal. For example, I have given an example on the screen at a gain of 1, simple unity gain with all resistors of equal value. A 0.1% mismatch in just one of the resistors will degrade the CMRR to a level of 66 dB, 1 part in 2000. Similarly, a source resistance imbalance of about 100 ohms will degrade CMRR by 6 dB. So, you find the effect of these tolerances of the resistors that we use in the circuit can also lead to a degradation of the CMRR. This we have to take note of. Therefore, in such applications you must be able to get very precise value of resistors, preferably 0.1% or even better. Okay. When you have the common mode input voltage, only you must have 0 output, because the CMRR will make sure that the common mode signals are not amplified. But because the resistors have tolerances plus or minus 1%, you would get a corresponding differential voltage produced by the common mode voltages, and that also will get amplified by the large differential gain of the differential amplifier, and therefore, that will also add to the already existing differential signal. Therefore, your signal will no more be purely due to the difference in signal that you apply at the input, but it is also due to some slight differences in the resistances and things like that. So, this we should avoid. So, I have tried to explain it in some more detail. The overall voltage gain, when the signal same signal drives both sides, both the input inverting input and the non-inverting input of the operational amplifier, is given by ACM, is completely the common mode. Therefore, the common mode gain, which is shown by A suffix Cm, common mode amplification, is equal to the gain corresponding to the inverting input plus the gain corresponding to the non-inverting input. In the previous figure differential amplifier that I showed, the inverting voltage gain is very simple. We all know that A inverting is equal to minus R2 by R1, simple inverting amplifier gain, and the non-inverting voltage gain also we know is 1 plus R2 by R1 if I apply at the positive terminal. But I will go back to the circuit and show you this. If I now ground this input, the inverting input, and give the voltage directly at this node, then you find the amplifier gain is 1 plus R2 by R1 times whatever input that you give here. But in the present configuration, you are giving the input at this point, and therefore, that is going to be divided by a potential divider formed by R1 prime and R2 prime. Therefore, the voltage here is going to be R2 divided by R1 plus R2 times this common mode signal at the non-inverting input. This will now be multiplied by 1 plus R2 by R1 to get the overall gain of the non-inverting amplifier. That is what I have written here. A non-inverting is equal to 1 plus R2 by R1, which is the basic gain of the non-inverting input, into multiplied by the ratio R2 prime divided by R1 plus R2 prime, which is coming because of the potential divider formed by R1 prime and R2 prime. So, this is the gain corresponding to the non-inverting voltage. So, if I now add the two, because I want to find out the total overall common mode gain, ACM is equal to A inverting plus A non-inverting, and that is when you take that non inverting, we have already got that, and we have to multiply by the corresponding R2 by corresponding to the inverting amplifier. Now we can derive this useful formula. For example, ACM is equal to plus or minus 2 delta R by R, where delta R by R is what is known as the tolerance, the change in resistance with reference to the actual magnitude for R1 is equal to R2. To make that, we have made all the resistors equal, R1 is equal to R2, then the common mode gain will be plus or minus 2 into delta R by R by us bringing in the variation in the resistor. So the common mode gain will be plus or minus 4 delta R by R when R1 very small compared to R2. This will be the gain, or what we can say is the maximum value to the minimum value, you can say plus or minus 2 into delta R by R and plus or minus 4 into delta R by R, the two extreme values within which the common mode gain can change, where the delta R by R is the tolerance of the resistors converted into the decimal equivalent that I already mentioned to you. So you can see the common mode gain can become a function of the tolerances of the resistors, and therefore if the tolerance of the resistor is taken care of, if it is 0.1% or something like that, then the overall performance will be better, because the common mode gain will be very much smaller at that stage. Right, I have just taken an example here in the circuit. So for example, if I have plus or minus 1% tolerance, what will be the variation? The common mode gain will be plus or minus 2 into delta by R for R1 is equal to R2, that will be plus or minus 2 into 1%, and 1% is 0.01. So that means plus or minus 0.02. And if R1 is very small compared to R2, it will be 4 times delta R by R, and that will give me 0.04 plus or minus as a common mode gain. So therefore the common mode voltage gain will lie between these two limits, either plus or minus 0.02 and plus or minus 0.04. And when R1 is equal to R2, the voltage gain, differential voltage gain, becomes minus 1, and the equation therefore total gives that plus or minus 2 into 0.1%, 2 into 0.001, and that is equal to plus or minus 0.002. This is the variation that you will get for the common mode, and the CMRR is AV by A common mode. This is 1 by 0.002, that is equal to 500. So this is equal, this 500 in numbers is equal to 54 dB. So the vertical bar here shows that is absolute values of the gain, that is what we are using without worrying about the sign. So 54 dB is the CMRR magnitude. So it has come down because of basically the tolerances of the resistors when I use 1% resistor. So in spite of these problems, still this configuration of a very simple differential amplifier like a subtractor, it is basically a subtracting amplifier, is one of the best simplest method of handling instrumentation signals coming from very low levels. And therefore if at all you want to build a better instrumentation amplifier, what you have to do is you should try to improve this configuration. One way to improve this configuration is by using buffers. You might remember at the beginning I was mentioning that the instrumentation amplifiers will have different impedances corresponding to the two inputs, inverting and uninverting. First let us try to address that issue and see how we can make the two impedances almost equal and large. One way to do that is to use a unity gain buffer. You can see on the screen we have used a unity gain buffer corresponding to both the inputs, one for the inverting input and another for the non-inverting input. And so instead of giving directly to this differential amplifier at the inputs, we have added two unity gain buffers, which we all know the unity gain buffer has got very high input impedance, non-inverting buffers, and therefore, they have very high input impedance, and they will almost be the same order in terms of input impedance, because it is very large, the difference is very small between them, and therefore, that takes care of the differences in the input impedance of the second stage, which is the normal differential amplifier that we discussed about. So, this 3 op amp configuration of the instrumentation amplifier is very useful. We will apply it in many situations. We will also see a demonstration at the end of a very similar configuration. You can also improve further this configuration. What we have done here is, for the earlier buffer we have made unity gain. You can also have a gain. In case you want, you can improve that by adding an additional gain. That is what is shown now on the screen. You find here it has become now a non-inverting amplifier with R5 and R6. Similarly, for the second input, you again R7 R8 forms another combination which will make the second input also as a non-inverting amplifier with a specific gain. The gain of the inverting input is 1 plus R5 by R8, and for the other one 1 plus R8 by R7. So, this will provide additional gain. You can have these resistors reasonably the same. For example, R5 and R8 can be same, R6 and R7 can be same. Thereby, you would have the same gain for the 2 input amplifiers, and then that amplified differential voltage will be applied to the difference amplifier, which is coming as the second stage. This is one of the classic designs of the instrumentation amplifier. Right. So, what we have done is, let us assume that R5 is equal to R8, R6 is equal to R7, and as before R1 is equal to R3 and R2 is equal to R4. R1 is equal to R3, R2 is equal to R4. So, try to maintain all the resistors equal as much as possible, so that the whole thing becomes simple to understand. So, V output then will be the difference in voltage V in 1 or V in 2 minus V in 1 multiplied by 1 plus R5 by R6 into R2 by R1. Previously, we had only R2 by R1, because we did not have the non-inverting gain stages at the input. Because we have a non-inverting gain stages, and because the gains are the same for both the inputs, you have 1 plus R5 by R6 coming there, which is now coming as a product term, and there is a sign change here to take care of the minus sign that we get from the amplifiers. So, this does increase the overall gain, because you have got additional gain stages at the input, and therefore, the overall differential gain also will increase, but at the same time the common mode signals also will get amplified by the 2 amplifiers. That is what you should remember. Now, another modification of that is, you replace the 2 independent resistors that used here, R5, R6 and R7 we used, and we replace it by one single Rg. That Rg will be R6 plus R7. So, that is what you use, and if you use all of them equal, then Rg will be twice that resistor that we used here. So, this again is a slight modification of the earlier circuit, and this also a very good configuration for instrumentation amplifier. This provides a further refinement, and therefore, it becomes a very popular design. What is a important improvement? Improvement is, as I told you, the 2 resistors R6 and R7 are replaced by one single resistor Rg, and that Rg can be varied to vary the gain or differential gain of the amplifier. A1, A2, which are the gain stages for the input buffer amplifiers, will make sure that you can see the voltage here is the same as the voltage here, right. In any op amp, the 2 inputs should be almost equal to each other. So, this will be the same, this here the same. Therefore, the common mode signals will appear across R6, but what is amplified will come here, and therefore, the differential input will come between these two input, which will be amplified by the second stage of difference amplifier. Now, therefore, if I now vary the R6, I will be able to vary the gain easily. So, this will also vary the common mode signal. Therefore, this resistor can be used to vary the CMRR of the amplifier also. So, the full differential input voltage will now appear across RG, because the voltage at the summing junction of the each amplifier is equal to the voltage applied to its positive input that I already mentioned to you. And since the amplified input at the output A1 and A2 appears differentially across the three resistors R5, RG and R6, the differential gain may be varied by just changing RG. So, that is one of the advantages of this circuit. Now, having talked about the various instrumentation amplifier and the refinement, we should also start wondering what will be the applications of these amplifiers. I already mentioned to you that they are useful in instrumentation amplifier. One of the simplest application that I can think of is a sensor. I have a sensor which is basically a resistive sensor. For example, light dependent resistor. The resistance varies depending upon the intensity of light falling on it, or you have a thermistor where the resistance depends on the temperature, or you have a strain gauge where the resistance depends on the stress applied on the system. So, all these things are resistive transducers or resistive sensors. So, if I have resistive sensors, the best way to convert the variation in resistance into a voltage, which is what we would like to have, because we can amplify voltages using amplifiers. We would like to convert the change in resistance due to the various parameters like light or temperature or strain into useful voltage, sensed voltage, and then amplify them. When you have such a problem, the best and the simplest technique is to put them in a normal well known Wheaton's bridge configuration, where you have 4 arms R1, R2, R3, R4, and you know R1 by R2 is equal to R3 by R4. So, when the bridge is balanced, the output voltage is 0. When there is an imbalance in the bridge due to a variation of one arm of the bridge, you get a corresponding voltage output which can be amplified, and if the variation is produced due to temperature or light intensity or stress or strain, you will get correspondingly an output which is proportional to that variation, and therefore, you are able to measure the temperature or the light intensity or the strain. So, that is the principle of the bridge amplifier, where the bridge amplifier is basically a differential amplifier, and better thing would be to use an instrumentation amplifier. So, I have shown on the screen how you can connect a Wheaton's bridge here corresponding to this simple differential input configuration corresponding to a instrumentation amplifier that we discussed. So, in the Wheaton's network, R1 by R2 is equal to R3 by R4. If any one of the resistor is going to change due to some parameters, being a sensor or a transducer, then the output of the amplifier will become proportional to that parameter. I have given a lot of examples of those transistors, and now I am showing you the complete circuit where I have this bridge here connected to plus 15 and minus ground across the diagonal points, and then you have the other diagonal point will be connected as the input for your instrumentation amplifier, which is again a 3 op amp instrumentation amplifier configuration. I have shown for typically in this circuit, I have taken all the resistors to be 1K, 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 and only one of them, which is a transducer, I have chosen to be 1K, and it can vary plus or minus by delta R, where the resistance change is proportional to the temperature or whatever. And so, that is what I have shown here in the circuit, and the output will now therefore be a differential input which is proportional to the change in resistance, and it will also have a common mode voltage which is going to be 15 volts divided by 2 resistors of almost equal value. So, the common mode voltage here will be around 7.5, half of 15 volts, and here also it will be very close to that, except for the variation that is going to come due to the change in the parameter, either transistor temperature or light or whatever. So, that is going to be amplified here, and because this has got good CMRR configuration as we discussed, you would find this will preferentially amplify only the change in the resistance here, assuming these resistors are very precise within 0.1 or 0.01% tolerance. Right. So, the common mode input is 0.5 times, because we have used 2 1K resistors across 15 volts, it will be 7.5 volts. Right. Now, what I would do is I will show you an actual circuit which is formed by 3 op amp with 2 buffers and the one of the difference amplifier. The other important point perhaps which I did not mention is that it is always convenient to have even the buffer amplifiers all in one single monolithic IC, rather than using 3 independent operational amplifier. So, instead of using 3 op amps, I have actually made use of LM324, which is a quad op amp. 4 op amps are there in that, and I have used 3 op amps for our purpose, for building an instrumentation amplifier. The advantage of having a single operational amplifier array is because the 2 input buffer op amps also are very close to each other, and therefore, they will have very good tracking characteristics. Their temperature differences and things like that will be very well taken care of, because they will become common mode signal. Now, they are very close to each other, and so anything that is common will be rejected by the difference amplifier, and if they are on the same monolithic chip, then it becomes all the more better in terms of performance. So, the suggestion is, instead of using 3 independent operational amplifier, it will be a good idea to use one single IC which has got either 3 or 4 op amps, and make use of 3 op amps for the instrumentation amplifier configuration. Now, I will quickly move over to the demonstration table and show you the working of a similar instrumentation amplifier configuration. So, I hope you can see the circuit is shown here. It has got a 3 op amp configuration with RG here, and it is also having a gain here, which is shown by R prime, R1, etc. We discussed about this. So, I have 2 op amps here, and the third op amp is a normal differential amplifier, and the input is given from a millivolt source, which is seen here. This is a standard millivolt source we have been using in all our experiments, and that is connected as the input here, and the output is monitored by making use of the multimeter. Right. And we have a dual supply at the back, which is providing the voltage for the circuit that you see here. I would like to show you also the circuit here. This is the LM324 operational quad operational amplifier circuit, and the various resistors and wiring is done exactly according to this configuration, which again is what I showed you before. And one of the resistor, that RG, which is at the middle, R prime, R these 2 R prime and these, they 3 come together, and this is the potentiometer, which is being used as the variable thing for changing the gain and the CMRR of the instrumentation amplifier configuration. So, the input is around 500 millivolts. If you see the it shows about 0.49, nearly about 500 millivolts or 0.5 volts. Now, let us measure the output. Output is around 0.2, because this resistance is in the lowest position. Now, I am going to increase the resistance. Now, you would find as I increase the resistance on the multimeter, the voltage is changing correspondingly. I hope so. Right. When I increase, it goes to 0.49 which is the maximum you can get for the corresponding to the resistors that I have used. I have used gain of 1 and therefore, you get 0.49 R2 by R1, everything is 10k here and therefore, you get a gain of 1. Right. So, by making use of this potentiometer, you will be able to change the gain and you can use this simple configuration as the instrumentation amplifier. Having seen this application of the operational amplifier, which is as an instrumentation amplifier, we will move on to another application of the operational amplifier, which is for driving larger current. In most of the applications you would find, especially for example, if you want to drive a solenoidal valve or a motor, things like that, you not only have to amplify the voltage, but you should also have enough current drive capacity for driving the motor or the solenoidal valve or whatever. So, unfortunately, if you take the 741 operational amplifier, you would find the short circuit current is around 25 milliamperes typically. So, that means what? Even if I connect the output of the operational amplifier to the ground, I will get a maximum of 25 milliamperes. Of course, if you keep it for long, the operational amplifier will be burnt out, but that gives also a limit to the maximum current that I can obtain from operational amplifier. That is rather low, 25 milliamperes. So, if I want more output current of the order of several hundreds of milliamperes or even amperes, then you have to go for power op amps. There are power op amps available. For example, I have given 2 typical numbers, LM675 or LM12, things like that. There are plenty from different manufacturers. You can refer to different data manuals and try to look for power op amps and then find what maximum current they can handle. But I can assure you they are rather expensive. So, is there a way by which I can use the same 741, which is rather inexpensive, simple to operate, very familiar to us also, but at the same time improve its current performance, with reference to output current? The answer is yes, and you can use a very simple scheme, and that is by using an additional transistor, the power transistor. If you use a power transistor which can handle higher current in combination with the 741 operational amplifier, then you can go to higher currents than 25 milliamperes. You can even go to 3 amperes or 10 amperes or whatever, and that way it becomes very inexpensive, because power transistors are not all that expensive. 741 is also not very expensive, and therefore, when I combine them, I will be able to get much higher currents for not very expensive scheme. So, this I call the current boosters. We can have a very simple configuration. I am going to talk about 2 types of current boosters. One is unidirectional current boosters, which is mostly used for some simple DC applications. So, I have shown a circuit here where I have used op amp in the non-inverting mode, as you can see, and the base of the transistor, which is a power transistor here, is connected to the output of the operational amplifier, and the collector of the NPN transistor is connected to the VCC, and the emitter is connected to the output point, to which I can connect the load RL. So, what I get across RL is the V output, and I can you have a V in here, and this R1 R2 forms a non-inverting configuration. Therefore, the gain of the non-inverting amplifier is R2 by R1 plus 1 or 1 plus R2 by R1, and you will have the output transistor, the output current from the op amp is used as the base current. The advantage of that is the transistor, we all know, has its own beta, the current gain, the HFE, and therefore, this output current from the operational amplifier is only the base current. you have to multiply by beta times to obtain the collector or the emitter current. So, you have another factor coming in, multiplication factor, which is able to boost the total current. So, there is also another important point here to recognize, and that is you find the emitter of the transistor is connected to the load. This is also very useful, because if you want a good voltage amplifier, the output of the voltage amplifier should be almost close to a ideal voltage source. That means its output impedance or output resistance should be very, very low. Now, the moment I bring in a transistor, how to maintain still a low output impedance? Usually 741 has got low output impedance of the order of 75 ohms or so, and so when I connect a transistor, I want to maintain that low resistance. For that, what I do is I use the transistor in the emitter follower mode or the common collector mode. So, you find the emitter is connected to the load. So, because of this, there is going to be a reduction in the output impedance, plus you also have a feedback, negative feedback, that also will bring down the output impedance. So, that is what I have shown here. Z output is going to be Z output of the normal amplifier divided by 1 plus A beta, where A is the gain, B is the feedback ratio. B in this case, because you have used R1 and R2, is R1 divided by R1 plus R2, R1 divided by R1 plus R2. So, the maximum load current is I max beta times the I short circuit current, the maximum current that I can get from the op amp, and beta DC, if I assume to be 100 for the amplifier, for the transistor, the beta for the transistor is 100, then I short circuit I mentioned is typically 25 milliampere. So, when you multiply that, you can get 2.5 amps. So, just by introducing a power transistor which has got a gain, current gain of about 100, you are able to improve the short circuit current or the maximum current that you can get from your op amp amplifier configuration from a simple 25 milliampere to 100 times more, 2.5 amperes. So, this is a very, very useful circuit for driving solenoid valves or things like that, motor, toy motor and things like that, and therefore, I thought I will discuss about this. So, I will just quickly show you the current boosting circuit. You can recognize this is the same circuit which I just now showed you. It is a non-inverting amplifier. The non-inverting input is the input for the voltage, and you have an R1 and R2 connected. This is 1k and this is 10k. So, there is a gain of 1 plus 10 by 1, that is 11, and 1k is also the load here presently connected. This is the transistor, and the transistor you can also see in the circuit is SL100. This is an SL100. This is the op amp, and the wiring is done exactly for this configuration. Now, I have got here, if you see, 3 resistors, because I wanted to show for 3 different resistors what is the output voltage. I do have the same 500 millivolts as my input voltage from the millivolt source. I have 500 millivolts as the input coming to the amplifier. The output of the amplifier is monitored by using a digital multimeter which shows 5.63. So, there is a gain of 10 times, because I have 11 times nearly 55, 500 multiplied by 11 is 5.5 volts. So, you can see there is already a gain here, 5.63 is very close to 5.5. That additional voltage is due to other aspects like the offset voltage, input bias current variation and things like that. Okay. Now, what I am going to do is I am going to just vary the load and show you. Now, I have connected 1k. Now, what I have done is I have removed the 1k resistor and I have connected a 470 ohm resistor as the load. So, as I change the load, the voltage should not change, the output voltage should remain constant. Now, you can see it is still 5.62 even when I change the load to a lower value, nearly half of the previous value. So, when I now again I am going to change that by to a different value, that is a larger value. So, now this is around 2.2 k. This is a 10 k resistor that I have connected here as the load, and even now the voltage is not very different, it is only slightly less 5.8. So, of course, there will be a limit how far we can go. If you go to very large resistors, then it will create problem. So, within a range you would find, even if you change the load, the output voltage remains a constant. That obviously shows the output behaves more like a voltage source, and whatever is the input, that is what I get at the output. Now, I am going to slightly increase the input voltage also from 500 to 600, and correspondingly you see the output voltage also is changing correspondingly. If I still increase, it goes to a new value, nearly 8 volts, and if I now bring it down, you find correspondingly the output voltage also decreases. So, now again it is 500 and it comes back to 5.8 at the output. At the output is 5.8. Now, it still further I decrease, it is now 400 millivolts and it is around 4.7. So, the output varies according to the input voltage whenever I change the voltage, but if I change the load by a range, you find the output does not change at all, it remains constant. So, that shows that this is a very good output driving stage, and because as I already told you, because the load comes in the emitter of the transistor, it becomes a emitter follower configuration, and thereby it produces a very low impedance and therefore very useful. Having done this unidirectional current booster, you would perhaps be wondering what will happen if I have a sinusoidal input, not a DC, but a AC input. Can I still have a drive which will be able to provide much higher current than what a simple operational amplifier can give you? This operational amplifier can give you only about 25 milliamperes as a short circuit current. So, let us try to modify the circuit to take care of the variation of the voltage on both sides. Even then you must have a large current provided both on the positive and the negative side. So, you can see on the screen a simple configuration. It is, if you find that it is cleverly constructed here with the two transistors, one is NPN, the other is PNP, in what is known as a push pull configuration, or in this case it is a complementary transistor. One is the NPN, the other is PNP. Both of them, both the emitters are connected together, and that is connected to the load RL, and the two output, the collectors of the two transistors are maintained at positive and negative voltages, plus and minus corresponding to the transistor. So, the output of the amplifier is connected, the operation amplifier is connected in parallel to the two base of the transistors, and the feedback comes to the emitter of the transistor. So, this is R1 by R2. So, this is an inverting configuration in this case for a change. The non-inverting input is grounded, the inverting input has R2 and R1 as the resistors. So, the amplifier gain will be minus R2 by R1. So, there will be a phase difference at the output as shown in this sign, and also because you have now two transistors, when the signal goes positive, the current will be drawn in this direction, and when the signal goes negative, the current will be drawn by the second transistor in the reverse direction. Therefore, both sides the current can swing with reference to the RL load, and it has got all the good features of the previous circuit which I showed as the current booster for unidirectional outputs, because again here the load is at the emitter of the two transistors. Therefore, it continues to remain in the emitter follower configuration, which always gives you low impedance at the output. So, what I am now going to show is a very similar circuit which is also called, as you know, push pull emitter follower, and it is in a class B operation, and the closed loop voltage gain is minus R2 by R1 because it is an inverting amplifier, and the output closed loop impedance will be divided by 1 plus A beta, where A is the gain of the amplifier, beta is the feedback ratio. Beta is R1 by R1 plus R2, and therefore A is minus R2 by R1. You can calculate and then correspondingly find out how much is the improvement, and the maximum load current again is the same as beta DC into ISC, which we have already seen. The maximum load current is the beta or the current gain of the transistor multiplied by the short circuit current. We assume the beta for both the transistors to be identical, which is normally true. If it is a matched pair, the two transistors will have the same beta, so it becomes very useful. So I have actually shown with a simple example. I have got a 51 kilo ohm resistors here and 1 kilo ohm, therefore the gain is around 50. In the figure, if a 741C is used for the op amp, what is the voltage gain of the circuit, what is the closed loop output impedance, and what is the short circuit load current of the circuit if each transistor has got a gain of 125, is a small typical numerical example. The gain is minus R2 by R1 voltage gain, that is minus 51 by 1, that is 51 is the gain. Feedback is 1 by 1 plus 51, that is equal to 0.0192, and therefore if the typical value of the output resistance is 75 ohms for 741, it is 1 plus A beta. A is 100,000 typical value of the gain multiplied by the beta 0.0192, and that 0.039 ohm, which is very small due to the feedback, and the maximum current is 25 into 125. They said 125 is the beta of the transistor, so if you multiply, it is 3.13 amperes. So you get a very low output impedance, and you also get a very high current, 3.13 amperes. So this circuit is very useful in several power amplifier circuits applications. So we will quickly see the demonstration now. You can see the circuit here, it is exactly same as the one which we discussed in a moment ago. This is a 1K resistor here, 51, here it is actually 110 kilo ohm, and therefore the gain is 10 minus R2 by R1. There is a minus that shows that there will be an inversion as shown by the sign, and you have the two transistors, this is SK and SL100 and SK100, these are the matched pair. If you want a higher current, you can always go for other power transistors which can handle much higher currents, and the emitters of the two are connected together and connected to a load here, and the input is given from a function generator around 500 hertz. This is actually the frequency, it is about 533 hertz, and that is a input given now to the transistor, and the output is monitored using an oscilloscope. You can see the oscilloscope, and you can see the two waves are slightly separated, and you can also see there is a 180 degree out of phase. When one is decreasing, the other one is increasing, when the one is increasing, the other is decreasing. So there is 180 degrees out of phase because it is an inverting configuration, and the amplitudes are almost same, and the actual amplification you say is about 10 times here in this amplification factor. So if I increase the amplitude, you would find correspondingly the output also changes. If I change here, the output also changes. That means both sides, the two transistors will automatically take care of the two swings of the input voltage to drive the load. The load here is around 1K. So you can change this load to any relay or any higher solenoid wall or whatever, and you will be able to drive it very easily up to about 2 amperes or so. So this current booster is also a very useful application. So today we have seen in this lecture that you can build good 3 operational amplifier instrumentation amplifier configuration for amplifying signals from sensors, resistive sensors in the form of Wheatstone's bridge or whatever, and we also saw 2 different configurations of current booster circuit, how the current output from a simple operational amplifier can be improved by using a pass transistor, either single NPN transistor or a matched pair NPN PNP combination in the push pull or complementary pair configuration and the emitter follower mode, and thereby you will be able to improve the current capability of the amplifier. Thank you.